of technology, and that was just about the time when it was becoming evident that machine learning is not just some, side tool, but that is actually a really powerful tool that is going to be used in a lot of places, including in earth sciences. And earthquake seismology is particularly has particular potential for machine learning methods because we have so much data. We're a very data-rich field. Even by computer science standards, if sometimes we tell the computer science how much labeled data we have, at first they think we made a counting mistake. So let me set up this. Okay, so today I want to give a brief, rather brief overview on machine learning and seismology. This is not going to be a comprehensive overview. It's a vast topic, and so I'm just going to show some examples that I think are interesting and necessary to maybe understand what is going on there. What I'm going to show, I'm going to start with the introduction and motivation, and then I'm going to try and introduce artificial neural networks, and then spend some more time on convolutional neural networks because they really are at the height of a lot of the things that we do today. I'm going to show how conv nets, as we call them, are useful in seismology. If we have time, but maybe this is too much and we'll have to skip it, I'll also show the example of signal denoising, and we'll see how far we can get. So let's get started with the introduction and motivation. A lot of advances in machine learning come from computer vision. And one task that is important in computer vision is how do you recognize objects in a fully automated and reliable way. And so you can ask yourself, how, for example, do you teach a computer to recognize cats? It's something that we humans are very good at. We see something, we immediately see this is a chair, this is a cat, this is a table. But actually teaching this to an algorithm has proven to be very, very difficult. And people have tried for decades without too much success. And so one way you could try and put this in an algorithm is you could try to, say a cat is something with paws and these pointed ears and a tail, and you can try to put that in some kind of equation, parameterize it. Or you could do a template matching approach where you take a lot of example picture of cats and then you sort of slide the image over a new image and see is there some, strong correlation somewhere. And you could say this is a cat. But what if we have to do with yoga cat? So cats come in a lot of different shapes and forms and colors. And so all of these approaches that we had before machine learning actually didn't work very well. So visual recognition is actually really hard because there's so many variations in images. So you can look at objects from different viewpoints. There can be different illumination conditions. There can be small and large examples of the same objects. They can be distorted, they can be hidden, they can be in front of some background that's confusing. And then there's a lot of intra-class variation. Also, there's a lot of different types of cats. And so any very simple and rigorous or not very flexible approach will not perform really well. But machine learning turns out, as we found out in the past decade or so, can do this really well. Now, there are a lot of definitions of what machine learning is, but one that I like is that machine learning is a class of powerful algorithms that can learn information directly from data without relying on a predetermined equation as a model. So to get back to the cat example, we don't need to find the cat equation. We can just train an algorithm to recognize how it finds cats in images if we have enough example data to train it from. And so it's the difference between machine learning and deep learning. Deep learning is a special case of machine learning where we use deeper models with more layers. I'm going to show in just a minute what I mean with that. Deep learning algorithms work on the raw input data directly. So for example, of cat images, rather than on features, on properties of the images. And so, for example, we can have a lot of cat images that we can train the algorithms with. And modern deep learning algorithms also use more efficient basis operations that I'm going to show you in the coming half or so hour. A famous example of machine learning advances is the ImageNet challenge. So it's the image classification challenge. It's a set of 1.4 million images, like the cat images, what we saw, but that we just saw. But it's not just cats in it. There's 1,000 different objects, and the task is to automatically classify these images. And not so long ago, in 2010, the best algorithm that won the competition had an error rate of about 28%. So every 1 in 3 or 1 in 4 images or objects that it was supposed to classify it wrong. And there was a big step when the deep convolutional neural network was first trained with a graphics processing unit in 2012. So the error rate came significantly down. This just continued until 2015. For the first time, they reached an error rate that is below what a human would accomplish. So if you asked a human to classify the same objects, they would make a mistake about 5% of the time. In 2015, the algorithm called ResNet for the first time beat that performance, so that the machine is actually better at this particular task than a human. In seismology, especially in earthquake seismology, we have been using these sort of algorithms, for example, to generate seismicity catalogs. And they sort of offer, the methods offer a new microscope with which we can image crustal deformation. This is an earthquake map from 2016 from Italy, from the central Apennines. There's been a sequence of damaging earthquakes with 3 magnitude 6 quakes. The largest was magnitude 6.5. Every dot here is an earthquake. The yellow star is the largest of the 3 main shocks. And now, if we use a deep convolutional neural network to process the same data to compute a new seismicity catalog, then the image looks like this. These are close to 1 million detected earthquakes that came out of the raw data. And this is just an example to show the difference that we can get if we use these new tools, and sort of the potential that this has. And so we get a lot more earthquakes with which we can detect faults. We can see if there's precursors. We can use them for tectonic interpretations, etc. We have a much better data basis, or basis of data products, rather, with which we can do our science. So this is why we want to study machine learning. We want to use machine learning algorithms to solve science problems. I would argue we also want to understand what the robots do. If you've followed the recent developments, for example, with the large language models and ChatGPT and so on, there's a lot of automation that can now be done that was unthinkable just a few years ago. And I would expect that this will become very prevalent, and I think we all want to be in a position where we can actually understand what these algorithms do. And what is possible today is really astonishing, and there's incredible progress, and there's, I think, no end in sight. And Andrew Ng, who has been a pioneer in the field, he was talking about this 1 second rule just a couple of years ago. So Andrew Ng, he's the founder of Coursera. He's I think, lecturer or professor at Stanford University. And he said, sort of on what machine learning models can do, he said, if a typical person can do a mental task with less than 1 second of thought, we can probably automate it using AI, either now or in the near future. And I think this quote is from about 2019 or 2020. So, for example, these the object classification tasks that I just talked about. So you can look at an image and you see right away, oh, that's a cat, or that's a boat, or that's a horse. We can do this very, very quickly. Anything more that would take us longer maybe wouldn't be possible with AI. And so from about the same time, here's some taxonomy of different types of machine learning. I'm going to talk a lot about supervised learning, where we have labeled data, so we can do very efficient and powerful classification and regression tasks. Another main branch is unsupervised learning, that is about clustering and dimensionality reduction. And then there's reinforcement learning from that is very important, for example, in robotics. Now, what is completely missing here is generative AI. Very few people in 2019 had generative models on their radar in 2019. And then along came things like large language models, ChatGPT, and so on, and it completely changed the picture. So today we would maybe draw this a bit differently. And so we have sort of this nested form where we have the neural networks and then deep learning. And then as a subtopic of deep learning, we have generative AI. And part of those are the large language models that just, swept the world and just showed how powerful or what we can do. I don't know if you've have beyond maybe ChatGPT had interactions with generative models. I can encourage you to try. This is a bit outdated now, but it's still pretty impressive. For example, if you go to thispersondoesnotexist.com, it will show you generated images of people that don't really exist. There's naturalreaders.com is for an example where you can generate voice from text. It's really astonishing what these algorithms can do. Here's an image or an animation that was made with the StyleGAN algorithm. And it's the underlying algorithm from thispersondoesnotexist.com. And it shows how data, in this case, portrait images can be generated from people that don't really exist. We do the same thing in seismology. We do this quake does not exist in that we generate seismograms that do not exist. This is something that Karek and I are working on at the moment. So one of these sets of seismograms is real and the other one is our synthetic seismograms. And these are conditional seismograms where we can say, well, we want seismograms for magnitude 6.5 earthquakes with a recording distance of 10 to 15 kilometers and soft side conditions. And then we have an algorithm that can give us any number of realistic seismograms with the same statistical properties as real seismograms. And we can use such synthesized data, for example, to do engineering studies for how would a building respond in this type of shaking. So there's a lot of rapid development of algorithms with which we can do a wide range of tasks. And there's a lot of potential in particular also for earthquake science. And so in the next segment, I would like to try and explain a bit how the basic principle of artificial neural networks work. And by the way, if anybody has, if something's not clear, please feel free to interrupt me at any point in time. I don't see if you raise your hand or something, but just you can just switch on the microphone and interrupt.
So if somebody raise their hand, I will try to stop your talk and then give the floor for the audience. Thank you.
Excellent, perfect. So artificial neural networks, how do they work? The underlying principle of artificial neural networks is that if we have a lot of labeled data, so data where we know what they are, we can learn an empirical mapping function between some input and some output for which we know that they're related, but we may not know how they're related. So for example, if we want to, we're a manufacturer of, say, I don't know, running shoes, we want to predict how many people are going to want to buy our shoes. Then we know that, this demand for our running shoes will depend maybe on the price, on shipping costs, on how we market it, on material, and so on. And all of this will affect demand, but not in a very straightforward way. There's sort of it may be quite complicated how people respond to all these different factors. And so with the neural network, we can learn how to do this. The neural network with what we call an input layer, where we have these what we call input features. So here there were price, shipping costs, marketing, material. Feed them in here. At every neuron, we compute the weighted sum of all these incoming connections for this particular neuron, plus what we call a bias term. And then we have some nonlinear activation function around this, which introduces a nonlinearity. And then we pass this on to the next neuron. At the next neuron, the same thing is going to happen. You compute the weighted sum from all the previous neurons. You feed that into the activation function with the nonlinearity, and then you pass it on, and you end up with a single output. And this could be, for example, the prediction for this demand for how many people are going to want to buy our shoes. Maybe it's easier if we start with an actual seismology example. So, for example, if we want to build a earthquake early warning system, where we have a quake, there's somewhere here, there's a quake starting, there's a place where a lot of people live, and where there's infrastructure. We have a seismic network of many stations. If we have a smart enough algorithm that recognizes, oh, this is an earthquake and it's a big one, we can potentially give a few seconds or maybe 10 seconds or so of warning time to the places that are at danger from this quake. And so the task then would be for the computer to determine if some seismogram is a P wave, so it could be coming from a real quake, or if it's just a noise signal, maybe a malfunction of the sensor or something like that. And because earthquake waves are so fast, we have to do this with only a very small amount of earthquake signal. And so one thing that we could do is we could compute features of this, say we have 3 seconds worth of seismogram. We need to decide, is this a raw quake or is it a noise signal? Then we can compute features from the input seismogram. For example, peak acceleration or peak velocity, or any other property of the signal that we think might tell us something if this is a real P wave or if it could be a noise signal. And then with these features, we can make a prediction. The classic way before machine learning would have been, for example, a linear classifier. So we would, do a linear classification scheme where we compute a weighted sum of these features, and then if this weighted sum is larger than a threshold value, we'd call this. We would predict that this is in fact a P wave, so we should send out an alert. And if this weighted sum is smaller, then we would think it's noise. And this works well if we have a linear problem, and when the two classes that we're interested in are what we call linearly separable. But in a lot of real world problems, these classes are not linearly separable. And so we can't just draw a line, a straight line that would separate these two classes. And to treat these nonlinear problems, neural networks actually turn out to work much, much better. And the neural network way of doing this would be that we compute the same features that we measured on these 3 seconds of seismogram. And we run this information through our network with these operations that I described earlier. And the output will be the probability that the input seismogram is a P wave rather than noise. And now, the reason why this works is because we have, or one reason why this works is because this equation has a lot of free parameters. So this network contains all these different weighted sums, and basically every connecting line between any two neurons is a weight. And that's a free parameter that we can tune. We can tune that so that we get the right answer. So that when we give it the features from a real P wave, it will say, this is a P wave. So for example, we could encode this by saying, if this number is close to 1, then it's a P wave. If it's close to 0, then it's noise. And we can train this, we can find the values W from all these different connections such that the algorithm close to always gives the right answer. So that it says 1 if we give it a P wave and 0 if we give it anything else. So this is the underlying principle of artificial neural networks. In seismology, we these days rarely use these very simple neural networks, but it's much more common to use other types of networks, for example, the convolutional neural networks, which have a number of important advances. So how do convolutional neural networks work? ConvNets, as we often call them, are actually a lot of fun. So you can do, for example, they're common in image processing techniques, and you can, for example, combine the style of some image with a style from an artwork and sort of merge the two. For example, you can give your house a sort of Van Gogh vibe. But you can also do not just fun things, but also very useful things. And the principle of convolutional neural networks is that they have not just these weighted sum operations, but also convolutional operations. So in this schematic, this bit here that is the one that we just saw down here is what we call a fully connected network, like the one that I just talked about, where we have, every neuron is connected with every other one. The lines are not shown here. And then at the end, it makes a prediction. In this example, this is a classification. So you want to know if the input image that we give it, and I should probably switch on my laser pointer. So we give it an image, and we want the algorithm to tell us this is a dog, a cat, a boat, or a bird. Now, before this fully connected neural network, we also have what we call convolutional layers. And what the convolutional layers do is they apply a large number of parallel and sequential digital filters to the input. And so before this becomes maybe a bit more clear, let's see what a convolution actually is. Many of you probably know this, but it's maybe to get everybody on the same page. It's useful to talk about convolutions briefly. So convolution operator is defined as shown in this formula, where we have a vector, a discrete vector y, n that is the result of the convolution of an input vector xn with hn. And we get yn as a sort of sliding window approximation. So for example, the input signal could be x naught until x5, and the filter h will be x naught, h naught, h1, and h2. And so to get y, we would just use the three filter operators and slide them over the input vector. So we always convolve h naught to h2 with the input vector in a sliding fashion. If you want to express this in terms of linear algebra, then this you realize that this is just a simple matrix operation that you can find very compact. H could, for example, be 1/3, if in which case this would just be a moving average filter. So if everyone, you have this 1/3 plus 1/3 plus 1/3 of three neighboring elements, that gives you the output will be a smoothed out version of the input vector. Now, this can also be done in 2D, and this is important for the images that we just saw. So you do the same thing, just slide over instead of a 1D filter. You have a 2D filter that you can slide over your image and get a particular output. Now, depending on how you choose these weights or these filter coefficients h, you can get a different result. So for example, you can have an identity filter that looks like this, with just one in the middle, and the output will be identical to the input. You could also have an edge detection filter that highlights where the edges are in the image, or you could make it a sharpen filter, or you could just use it to blur the filters. You can get a lot of different properties out of an image by choosing certain filter coefficients, h here. And then with these filters, you slide them over your image, and then you get what you call a feature map, and that's then passed on in your neural network to the next level. Now, the fundamental point of convolutional neural network is that we don't have to choose these filters ourselves. We don't have to engineer what h is, but we can learn from the data what these filters should be. So in the network that I showed earlier, these are all convolution operations where we slide this filter over some input image, and then we get these feature maps. We have a couple of parallel such filters, so we apply different filters at the same level. Then what we do is pooling, which is to downscale the image a bit, and then we repeat this. There's also activation steps in between to introduce nonlinearities. But fundamentally, we apply these filters both sequentially and in parallel. And now if we have a lot of examples of images where we know what the right label is, so we have an image with an according label, in this case, both, then we can use an optimization algorithm for to find the right filter coefficients H, so that at the end of the day, you get the right answer. So that here, indeed, the both class has the highest probability if we give the algorithm the image of a boat. And so these convnets can learn what features are relevant for the task for which the network's trained. It's a sort of automated feature extraction system, and people have been wanting to get there since the 1950s, but it wasn't possible until about 2012 to actually do this. And that was the breakthrough that then came with larger computers, larger data sets, GPU computing, and some methodological advances. And when I showed you earlier this ImageNet classification challenge, you see that the big breakthroughs started coming here with the deep convolutional neural network. So they're algorithms of that type. Okay. So now that we know a bit what a convolutional neural network is, we can see how we can use the convnets in seismology. And seismology, convnets have been tremendously useful in seismology, and there continue to be, new methods coming out that do an ever better job at working with seismic data. Often we use, for example, seismicity catalogs to study tectonics. So this is an example of the Japan subduction zone with the Great Tohoku earthquake, and we can, for example, use seismicity to see the geometry of the subducting plate. But as you all know, the data that we have, our data aren't the catalogs, but our data are the waveforms. So we need to go from the raw data, the waveforms, to the seismicity catalogs. This is an image, this is a 12-hour seismogram of the magnitude 7 Ridgecrest earthquake in California. So it's a drum plot where you go along one line and then it connects again over here. You see here a couple of foreshocks, and then the main shock is here in blue. For hours and hours after that, we have thousands and thousands of small quakes that all tell us something about the crustal deformation processes. So if we want to build a seismicity catalog, we need to find, identify, and exactly label all of these seismic phases. So it's a very difficult task, and something that also we've been trying to automate for decades, essentially, ever since we had computers. Now, the earthquake monitoring workflow to go from raw waveform data to seismicity catalog includes a lot of steps. So we want to do signal pre-processing, we want to do signal detection, we need to detect and identify the seismic phases, then we do phase association to see which phases belong to the same earthquake, then we want to do hypercenter location, and so on. So there's a lot of steps. Almost all of these steps have been improved in one way or another with machine learning methods. And so with machine learning, we get much better seismicity catalogs, which then we can use to study crustal deformation processes. And so I already showed this, this comparison from the Central Apennines in Italy from the Berosa et al. 2021 Nature Communications paper. This is an impressive study from Ross et al. 2010, where they have this swarm on a fault, where you see incredible detail on the fault as it goes, it dips down into the crust. So they can actually map out the topography of this fault zone and infer fluid migration processes in a level of detail that really wasn't possible before machine learning offered these new ways of computing seismicity catalogs. So how do we go from this image classification task to a seismology task? It's actually relatively straightforward because we can do almost one to one the same thing. So in an image class, you have a 3-channel, two-dimensional image. So you have, red, green, and blue channels. And we just have 3 spatial components. So we have a seismogram, we have, the 3 spatial components. It's basically, we can treat it as like a 1D image. We don't have 2 dimensions, but 1 dimension, so it simplifies a bit. But it's the same thing. So we apply these digital filters sequentially and also in parallel. We do the downsampling. We repeat the thing as many times as we want. At the end, we just write it all into one large vector. And then we feed it into the fully connected neural network. And then we can have whatever output we want to train this network to do. In this case, so this was one of our first attempts when we realized, we can take these, image classification algorithms and just turn them into seismology algorithms. And so here we wanted to compute the probability that an input seismogram would be a P wave or an S wave or noise. And so these numbers would sum up to 1. And if it's a clear P wave, then hopefully this number will be close to 1 and the other 2 will be close to 0, and vice versa. I think I said all that. Yeah. And then when we have this algorithm, we have it trained because we have a lot of labeled seismic data with which we can train all the weights in the network. Yeah, maybe I should say this one more time. So all of these filters that we apply here, they have the free parameters, the weights, also here, the connections between the nodes. These are free parameters that we need to optimize. And we do this by using large numbers of example data. And so, for example, in the Southern California seismic network, we had on the order of 20 million hand-labeled seismograms. And so we can constrain these weights really well because we can just show the algorithm a ton of example seismograms with the answer that it should get, that the algorithm should then predict. And the algorithm can then, through optimization, learn what these filters should be so that the right answer comes out at the end. Once we've trained the algorithm, and then you can apply it sort of in a sliding window fashion to any input seismogram, then you see how the P wave probability here in red goes up as soon as the P wave comes. And then at some point the S wave comes, the P wave probability goes down, S wave probability goes up. And then at some point the event is over, and then the probabilities are back to mostly noise. So you can apply this to, yeah.
Sorry to interrupt. There is one question. How do we determine the number of filter for each layer?
That is an excellent and a difficult question. There's no, people say this is a bit more art than science. So there's some rules of thumb that you can try to follow, but at the end of the day, it's a lot of trial and error. So in general, the more data you have, the deeper, the larger a network you can afford. And then there's some rules of thumb for how many filter coefficients you should have at any particular layer. But this is really just rules of thumb, and it's a lot of intuition and playing around with different types of models. One of the really nice things about this field is that it's an incredible openness of methods and data sets. So everybody puts their codes online. Everything's a large fraction of the machine learning models out there are available online. So you can see how other people have done it. They've probably tried a lot of things, and so you may want to try and find something similar, and then you can deviate from it to see if you can improve the performance. But often, somebody's already kind of found what is the right way to go for a particular problem.
Yeah, thanks.
So thanks for the question. Here's what it looks like when we apply this to a swarm in Southern California. You see every time it's red, it means that the algorithm detected a P wave. and every time it's blue, it's detected an S wave. And it's quite impressive to see how this algorithm manages to pick up, for example, this particular phase that is hidden in the coda of a previous quake. It still recognizes that this is a P wave followed by an S phase. And so more simple detection algorithms, like for example, SDA, LTA based algorithms, would be completely blind after something like this, and therefore fail to detect a lot of the quakes that are actually in the data. Another important advantage of these type of algorithms are also their flexibility. So I've shown you how we can use this ConvNet for a signal classification task, where we say we want to know if the signal is a P wave, S wave, or noise. We can also train almost the exact same network for a completely different task. For example, to determine first motion polarities. So if we want to determine, for example, if we want to compute focal mechanisms and we want to determine if the seismogram motion is first up or down, we can use the same network, just train it with different data and just train it to predict whether the first motion is up, down, or unknown. You don't need to change almost anything else. Maybe you want to play around with it a bit to see if the new problem works better with different hyperparameters, but essentially you can use the same algorithm for a completely different problem. And so we've done this in different places in Southern California or in the central Italy, central Apennines Italy sequence that I already shown. And so for those maybe who don't know, we use first motion polarities to determine the orientation of the fault and the sense of the slip. And so for this, we need to determine at the large number of stations if the first seismogram excursion is down or if it's up. And if we have enough of these recordings, then we can back out the direction of slip in which, or the fault geometry and the direction of slip. This looks very simple in this textbook example. So this, you would maybe thinking that this is easy to automate just because it's very obvious. And but this is just a textbook example. Most of our data is not like that, but instead we have low signal noise ratios, and then it actually becomes relatively difficult. And it turns out that this has been notoriously difficult to automate it. But with deep learning, this works fantastically well. So we can get we get almost no false positives, even for low signal noise ratios, and we have good few missed cases for as soon as we have relatively reasonable signal noise ratios. And so what we've done is we've done this with a lot of data, for example, the central Apennines, and computed a lot of focal mechanisms using standard algorithms like, for example, the Heidebeck and Shear hash algorithm. This is the result from the Amatrice sequence in the central Apennines. So there was Tan et al. I'm sorry, I dropped out the reference for this. It's Tan et al. In the seismic record from, I believe, 2021. Used PhaseNet, which is a convolutional neural network, to detect 14 million seismic phases in a 1-year time period. From this, they've been able to locate close to 1 million earthquakes. And now we've taken that data, ran another convolutional neural network on it to compute 56,000 such focal mechanisms. So you see here down here, the magnitude versus time over this time period of 1 year. These are all the quakes that Tan et al. Found. And so if we overlay the focal mechanisms, we see that now we have focal mechanisms from the entire time duration and down to basically magnitude 0. Now, mind you, the focal mechanisms are much, much fewer. They're only like 5 to 6%, so 56,000 focal mechanisms out of 1 million quakes. So we still only have some, 5, 6% of quakes have a focal mechanism, but we have a huge range of focal mechanisms. They cover the entire area, the entire depth range, the entire magnitude range. And so we have a lot more focal mechanisms to basically study the tectonics of this region. And one interesting, for example, that we found is that we have a very clear depth dependence of faulting styles. So this is an extensional regime where we expect normal faulting, and normal faulting is shown here in red with rakes that are close to -90. And we found that this dominant normal faulting is prominent only in a depth range of maybe 2 to 9 kilometers. And above that and below that, we actually have different typical faulting styles, including thrust faulting, that we find at very shallow depths. And this is probably because for normal faulting, you need a minimum amount of overburden for the vertical compressive stresses to become dominant, so that normal faulting would become the dominant mechanism. At more shallow depth, the horizontal stresses may actually dominate your stress field. And so before this study in this area, there were a little bit less than 500 focal mechanisms available, or those are actually moment tensors. And now we have 56,000 focal mechanisms to basically study the same thing, so we can discover a lot of interesting patterns. Now, the networks that I've shown you so far, they're sort of standard convolutional neural networks that have this these convolutional layers and then the fully connected layers in the end, which is what we started with when I introduced the artificial neural networks in general. More recently, people have started skipping this part and design what are called fully convolutional neural networks. And so they do these convolutional steps, including with the pooling or downsampling. And then you start doing the opposite again, where you start expanding again and end up with a prediction of the same size as your input. And so you don't even do the fully convolutional, fully connected bit at all. You can do this, for example, as a picker. So this is the PhaseNet algorithm that then, instead of just predicting P or S, it actually predicts a time series of the same length as the input seismogram and says, well, this is the probability of a P pick. So you can also use this to quantify the uncertainty in your pick, which you can then potentially propagate to your location algorithm. People have also started doing transformer architecture that have a self-retention mechanism. This is the big breakthrough that led to things like ChatGPT and all sorts of other much more powerful advances. And so here you have what is called an encoding layer, where you have a lot of convolutional layers, residual layers, and then you get sort of this latent representation, we call it. It's sort of a more condensed or compressed version of the input data. And from this on, you can do different tasks actually simultaneously. So you can do phase detection, you can pick P phase, S phases, and so on. So these are just a couple of use cases of how we can use convnets in seismology. And now I'm not sure if we still have time for signal denoising. Maybe I'll go through just very quickly. So this is actually a study that doesn't work with earthquakes, but with Marsquakes. The NASA space agency has put a seismometer on Mars in 2019 with the InSight mission. And this is work by a PhD student, or the former PhD student, I should say. Nicodemus graduated a couple of months ago. He's now a postdoc here at ETH. And he's shown how we can use convolutional neural networks to denoise this Mars data. The Mars data is quite noisy because for various reasons, but especially because there's strong winds. So this is an animation of the noise in the data. And he then used a fully convolutional neural network to denoise these noisy records. So you start with some 3-component seismogram that has a lot of noise in it. You do a short-term Fourier transform to get a spectrogram with the real and imaginary part for each of the 3 components. And then you can design a fully convolutional neural network that separates noise from signal. And so you do this by predicting what is called a segmentation mask that has values between 0 and 1. That's the same dimensions as the input data. And whenever the algorithm thinks that this is just noise, then it is close to 1. in this case here in the black. And when the algorithm thinks it's signal, then close to 1 will be here in the signal mask. Once you've predicted this mask for this particular signal, then you can just multiply the two, the input. So these are the same, these are just the spectrograms of the input. You multiply it with the segmentation mask, you do an inverse short-term Fourier transform, and then you get a noise waveform and a denoised event waveform. And this, we trained this mostly with synthetics in this case. Now we're trying to do it with real data on Earth. And it's incredible how well this works, that you can just basically, to a large extent, take out the noise from a noisy signal. And what we've done is, we found actually 60% more events than we had in the previous catalog, which was a very careful, manually produced catalog. And now you may be skeptical that this really works reliably, and I hope you're skeptical. And we were skeptical too, and we started investigating, how much these denoising segmentation masks distort the signal. And this is a bit too complicated to explain here, but the crux of the method is that the denoising method actually distorts the filter less than a commonly used Butterworth bandpass filter. So almost everybody in seismology uses Butterworth filters, and we always apply these to the signals, and we think it's fine. When we do this with synthetics, we actually find that the denoised synthetics are closer to the input signal than when we apply a bandpass filter. And so maybe the distortion of these signals is not so bad, but of course we should always be careful when we do this sort of thing. So we called this algorithm MarsQuakeNet, and it denoised this Mars mission data, and we used it to increase the size of a already carefully crafted manual seismicity catalog by over 60%. This is described in Dahmen et al. 2022 and JJ Planets, and it's just a new paper been accepted where we sort of go into a bit more detail on how these signals look. If you look up Nico Dahmen, then you will find also the new paper. And yeah, the deep learning denoiser distorts the signal less than a commonly used Butterworth filter. So this brings me to the end. A few short summarizing remarks. Essentially, machine learning methods allow us to make more of our raw data. So they're not a magic box that give us seismology, science results right away, but they let us make more of the raw data. And for example, with these seismicity monitoring algorithms, we can get better data products, such as seismicity catalog, which we can then use to study crustal deformation processes with these more standard methods. There's really an explosion of methods, and it's ongoing, no end in sight. New incredible stuff is coming out frequently still. And of course, we need to carefully investigate the results. And this is also challenging to make sure that we don't interpret some, artifacts from the algorithms. And with that, I would like to thank you very much for your attention, and I hope it was interesting. Thank you.
Great. Thank you, Menandrin, for a very insightful presentations. We learned a lot this morning in Zurich and then this afternoon in Indonesia. So now we open for question and answer related to what Menandrin has shown. So I opened first 3 questions. If you want to ask a question, please raise your hand, and then I will open the microphone for you, or you can unmute yourself. Yeah, Prof. Rishananto Kurnia from BRIN. Could you open your mic, please? Yeah.
Thank you, Dr. Meyer. It is very interesting presentation.
Thank you.
I just want to something like curiosity, because I saw that your presentation is about how to recognize and differentiate between P waves, S waves, and noise, but nothing to do with something like mitigation. Suppose in the area there is a earthquake occur, what happened with the surrounding? It's just I think the only to differentiate the P wave, P wave, S wave, and noise. Yeah, not for the other. Okay, thank you. That's all. Just curiosity only. Thank you for the nice presentation.
Thank you very much. So I focused on seismicity monitoring. I think it's it's a lot of what I do, and I think it's very good to explain also the methods. But we also do things that are relevant for hazard estimates and applications. So, for example, the generative models that we do, where we produce synthetic waveforms, one of the prime motivation is that we can use that to do better hazard studies and earthquake engineering, where we have right now we're very limited in the amount of data that we have for building simulations, especially for large magnitudes, short recording distances, and extreme site conditions. With these algorithms, we can potentially produce very realistic and basically unlimited numbers of seismograms that we can then basically run, for example, building models through to see how they would perform in such particular cases. Yeah, so we also do have the applications in mind. For example, the earthquake early warning is also, I think, a practically relevant outcome of this.
Okay, thank you. Thank you, Moderator.
Yeah. Thank you, Professor Haris Hananto. Is there any other questions related to the presentation today? So, okay, Omar Abdul Jabbar, could you please unmute yourself and then ask the question? Thank you.
Yes, sir. I have two questions in here. What can we analyze from the prediction result like U and test wave? Another from MATBAS like the model is maybe underperform or from what is from the best geophysics like maybe like noise, background noise, or amplitude signature ratio. That's and the second is how do we choose the algorithm and transformation to use to create a model? Like Evidence is use a combination of CNN, LTM, and use transformation to assist SCM for classifying. That's two questions.
I didn't fully understand the question, fortunately. The line's breaking up a bit. I think you asked how to choose algorithms, and I think to combine CNNs and LSTMs.
How we choose to make the model what the results.
So, Omar, we have difficulties to hear your voice clearly. So perhaps you can write in the chat to make sure that we understand clearly your questions. So I'm sorry for that because we really don't hear you clearly here.
Great.
Yeah. So yeah, I would really appreciate that. Thank you. So we have another question here in the chat. Is the noise similar to high pass filter? Can you explain a little bit more?
Is the noise similar to high pass filter? So both, I think, have to some extent the same goal. So when we apply any filter, then we want to usually get rid of the noise. But the noise can be at any frequency range. So it's arguably more than a high pass filter. The denoising algorithm basically gets rid of any signal characteristic that you trained it to not pay attention to. So in our case, we use synthetic seismograms that we computed with something like the Bohr method, stochastic method. And then we perturb that with a lot of empirical noise that is actually from Mars, from time periods when there's no quake. And this can include, low period oscillations. It can include spikes, or they also have a strong eigenmode of the lander that you see very well in the seismograms. And all of this, you can train the algorithm to basically take out.
So I hope Mr. Nugra is clear with your questions. So is there any other question related to that? If not, I may ask the questions. So, Menandrin, so we have advancement in the method of machine learning nowadays, and many published report, especially with face recognitions, event recognition, and then face picker. So, but I don't know, probably of my limited idea, is there any real-time implementation of these deep learning methods into daily routine of the early warning system, or with a continuous system in SCAT, for example, or any other agency out there? Do you know if there's any?
I don't think in terms of standard products. I'm sure it's in the making in numerous institutions around the world, including here at the Swiss Seismological Service. I'm sure that the Southern California Seismic Network is working in that direction, and the Northern California Seismic Network, for that matter. It's kind of an obvious thing to do, but it also, before it's ready for prime time and production in real time, it's a big step to take. And so I'm sure a lot of people are working on it. I'm not aware of any institute that uses this routinely already.
Yeah, that's what I'm thinking too. I'm wondering if there is any bottleneck currently, because I've seen that many methods perform very well with their training data, but I'm not sure with the upcoming new recorded data it will be works as good as during the training data set. So
yeah,
thank you.
Definitely.
Yeah. Mm-hmm.
This is definitely something that needs to be checked. I think the algorithms can be trained so that they will perform well also on seal data. And there are some bottlenecks, but nothing like fundamental. There's it's computationally more intensive, but we have big enough computers. It's just that there's a lot of steps that have been established over decades, and now we want to replace basically much of that. And there's a ton of different design choices that you have to be very careful about in order to make really things better and not introduce errors.
Yeah, so that will be very interesting for the future mitigation, especially in the region that is actively producing earthquake in Indonesia. We really have to implement like a very fast further analysis of the earthquake in order to avoid a very destructive consequences afterwards. So here I have another question. This is by Omar. So first question, how do we choose the algorithm and transformation to use to create a model like earthquake trans use a combination of CNN and LSTM and transformation to assist LSTM for classification? And then he has a second question. What can we analyze from the prediction result like P and S waves from the geophysics base?
So to the first question, there is again no clear answer. Like for some types of data, a certain algorithm choice, for example, recurrent neural network or a convolutional neural network make more sense. But it's just experience for the most part. There's no a priori reason why something would be better. For example, in seismology, we work with time series data. So a lot of people from outside seismology or data scientists would say, well, why don't you use recurrent neural networks? They're made for time series data. For some reason that we don't quite understand, convolutional neural networks work better in our particular field. And so we have tried to use the recurrent neural networks, but they are not as good for most of our purposes as the convolutional neural networks. And the earthquake transformer algorithm that you mentioned in your question is actually one of the few examples where somebody uses, at least in some places, recurrent neural network bits. But most of it is convolutional neural networks. And so it's experience, it's playing with the data, it's trying things out and learning from the things that other people have tried. And I didn't quite understand the second question, to be honest.
Yeah, me too. I don't quite understand what this. So, we have another questions from Inder. So, could you please ask your question?
Yeah, thank you very much, Pak Kadek. So I would like to ask that I have done a research to determine a hypocenter, but in Indonesia we have a limitation in the station. Let's say, for example, that an earthquake is recorded by 3 stations, let's say ABC, and the other earthquake is recorded by different station like DEF. So is it still representative if we want to determine the hypocenter with the different station? That's my question. Thank you, Mr. Mayor.
Thank you very much for the question. I think the answer is that it depends on how you design the algorithm. One of the key advances of the algorithms that I showed is exactly that they're general, that they're not dependent on any particular station. So there is ways to train it such that it would not depend on or design the network rather than train the network in a way that it applies to all stations and station combinations. Now, for the particular example that you mentioned with the hypocenter location, I have no experience with, to be honest. So I wouldn't quite know how to do it, but at least for the signal processing methods, it's one of the nice things about the algorithms that they're general, not specific to one station. I was thinking about, presumably you must have a lot of offshore seismicity, and then one-sided station coverage where the epicenter is always to one side of all the stations. And so among the interesting things that I've seen for this context is that people use neural networks to estimate the back azimuth and the distance for individual stations. And you could sort of combine these beams that you get to locate offshore quakes. I don't know if that would work very well, but it's something that I'm curious if that would actually be a promising approach. Yeah, these distance and back azimuth estimates, they're much better from the neural networks than previous non-machine learning methods. That's why I'm thinking it could have quite a bit of potential.
Okay, Dr. Mayor, excuse me, moderator, can I ask one more question, please?
Sure.
Okay, yeah, Dr. Mayor, I have a dream actually, because in other science, something like in the weather, we can forecast, and it happen accurately. And in the future, we hope that maybe, I don't know what kind of method to predict earthquake, especially in Indonesia is very high prone to earthquake. I think it's very, you can maybe suppose 1 day or 2 days before it happen, we just move away from the affected area. Just my dream actually. Thank you.
Yeah, this is an important point, and people are studying this and have had promising results in laboratory experiments where they can, predict the state of the fault and how close it is to failure, and therefore also the time to failure. And so this works in the lab if it works at the natural scale of natural earthquakes. Is not clear at the moment. I know that certain people are studying this and trying to make it work. It'd be fantastic if it does work, but it's predicting quakes is a lot more difficult than predicting weather, as you know, I'm sure, for various reasons. One of the things is that quakes are avalanche-like phenomena that can just grow out of control very quickly, whereas the weather tends to evolve more slowly and is therefore more predictable. But there is hope. People are studying it, and we'll see in the coming years if that bears fruit.
Yeah, thank you.
Yeah, thank you everyone for a very nice question and very interesting questions. Thank you also for very insightful presentation. So before we end up this webinar, I would like everyone that has a camera on their devices to open their camera for for us to do a photo session together. It is a lot. Please, Mr. Dehaene, could you please lead the process? Thank you.
Yes. Okay, everyone, please turn on your camera. We will wait in 5 seconds.
So Bernard, actually, the participants here are very enthusiastic because we have more than 90 participants today. They're talking to your
Yeah, yeah.
presentation.
Yes.
That's great to hear. Thanks a lot for your interest.
Okay. I will take in 3, 2, 1. Okay.
Thank you very much, Mr. Dehaene. So once again, and Andrin, thank you for your time, for 1 hour of your time, sharing information with all Indonesians here. So I hope many Indonesian or young scientists or also current scientists to pursue forward in the area of machine learning, and then with the rich data that we have in Indonesia, and also many earthquakes that we have in Indonesia, perhaps this machine learning could, especially routine processing, to work better and faster in order to process the data in a better way. So thank you, everyone, for your time. And then this is the certificate for Menandin. I will send you the PDF if you want it.
Thanks so much.
Thanks again, Menandin and everybody. I hope you have a very nice afternoon today, and then hope to see you soon next week, Menandin.
Excellent.
Thank you.
Looking
Thank
forward to
you.
that. Thank you, everybody.
Everybody.
Bye.
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 So let's close this 5, 4, 3, 2, 1.